So synchronous generators, we're going to be converting mechanical power to electrical power. So for this particular lab, and the reason why we really have to do this one online for all the groups is the prime mover for this device is pretty essential to making this work. The prime mover is the mechanical source of energy. And in this case, we're going to be using this 4-quadrant power dynamometer. And it's basically something that allows you to actually control speed pretty actively. Now, the way to make this device work is you have to mechanically interconnect this device to this device, which means we need a pulley or a belt between the two. So if you right-click on the module and you hit lower front panel, and then you do the same thing for the next panel, and then sometimes it's kind of tricky, but if you drag a line, you got to kind of find a spot. Sometimes it goes this way. Here we go. You can see I've got a line, and if I run that over here, it's actually going to go ahead and connect the belt. So this is exactly how we would be in lab, that you have a belt between the two, and then this is the belt tensioner. This is the one that keeps the belt taut so that it doesn't slip between these two shafts here. So once you're done, you lower up or raise the front panel. Raise the front panel. And you're good to go ahead and start connecting the device. So on the first figure that we do at the lab, which is figure 2, we have a prime mover that we're going to take our power to. So we're going to run those to a fixed DC source. Okay. And technically, we don't even need that because we're going to be running it in this mode here, which means we'd actually plug it here, but we'll kind of follow along. So we've got our power going in here. Now we're going to be monitoring the voltages, the 3 voltages out of the synchronous generator, and they're going to be connected in a Y. So the first thing I'm going to do is connect these two in their Y connection. And then I'm going to monitor each one of these, E1, E2, and E3 here. Now I have to provide a connection. So this terminal here is going to connect to the neutral. So let me just drag that down so you can see that. And now once I've got this neutral connection point over here, I can just simply run my connection wires here. And here, oops. So I've got my voltages all connected to monitoring. Now the only thing I need to do is monitor the current going into this synchronous motor. And I'm going to run that through I3. So I'm going to come out of my fixed DC into I3. So plus terminal 8. Then I'm continuing because it's a series circuit. This goes into terminal 7. And then I'm going to return back to the neutral connection here. And now I have this set up pretty much ready for lab 1. So for lab 1, I'm going to go ahead and I'm going to get the machine operating so that it is around, let's see, 1800 RPM, because if you look at the synchronous speed, the nominal speed for the synchronous machine, it's 1800 RPM. So I'm going to use my 4-quadrant dynamometer power supply to go ahead and do that. If you look over here, can everybody see this little power switch?
Yeah.
When I turn this on, look at what happens to this symbol here. It's no longer grayed. Now I can click it, and this is going to be the fancy controls for that device. So I'm going to change that to, I want that to be a constant speed, clockwise prime mover brake. And this is going to allow me to set my speed very efficiently here to 1800. That's the nominal speed. I'm going to go ahead and start it. And you'll see how it takes it over, it overshoots a little bit, but eventually will work its way down to 1800 RPM and stabilizes out. All right, so that's it. That's all you have to do at this point for the speed on it. And if you look over here, you can actually see that it's rotating. Now what I want to do is I'm going to go ahead and I'm going to look at my oscilloscope. So my oscilloscope is here. And I'm going to look at the voltage waveforms. Channel X, channel 1 is the X channel. So that's the X-axis. We're only going to be doing time for our X-axis. And our voltages are going to be E1, E2, and E3. I'm going to turn on my continuous refresh. And what's happening here? Why don't I see any voltage? What's the issue perhaps here? I've got power going to my data acquisition device, so there's power there. Why am I not getting any values there? Any thoughts? Well, all I have in this thing is, if I lower the front panel, I have this rotating element here, but I have no magnetic field. So remember we talked about EA equals K times phi times omega. I don't have, let me raise this. I don't have a phi, because where I get the magnetic field on the rotor circuit or the rotating part is through here. So I have to flip this switch on. Then I turn this device on, and let me shrink that so you can actually see what happens when I flip the switch on. Look at what happens to the voltages. There they are. Okay, they're a little low, 100. So I'm going to go ahead and increase these till I get to about 100. And let's say 120 volts. Pretty close. And those are my voltages. Okay. So a couple of things, right? These are a lot of waveforms. If I want to, I can change my time base to 2 milliseconds per division. And now I can see the different waveforms. I see channel 2 is sort of the light blue waveform. Channel 3 is the redder, or purplish, pinkish, whatever waveform. And channel 4 is the red waveform. And you can see that they're all about 120 volts, give or take. You can also see that I have a frequency of 60 hertz, but I don't actually have any angles. So what I'm going to do is I'm going to go ahead and I'm going to turn off this, and I'm going to use my cursors and actually look and see what the difference is between two successive peaks. So between these two cursors, it's off a little bit. Over here. That looks pretty darn close. My time difference between the two cursors is 5.45 milliseconds. Is that equivalent to 120 degrees? Is 5.45 milliseconds 120 degrees?
Yes.
How do you know? Or how can you tell? Can I give you a little help?
You see the difference in would it be the difference from, I don't know.
Well, first off, one way you can look at it, you know that at every 360 degrees, it completes a sine wave, right? So about here to here, it's 360 degrees. And it looks like that's about a third of the way, that's about a third of the way to another third. So it looks just physically like it's 120 degrees. But the other way that you can tell is this is 5.45 milliseconds. How many milliseconds does it take to go for one complete cycle? Remember, 16 hertz, what's the period of 60 hertz? So F equals 60, right? And my period is equal to 1 divided by F, isn't it? So it takes about 16.7 milliseconds, give or take, to go one complete cycle or 360 degrees. I have 5.45 milliseconds to go, but I need 16.6 seconds. So I can set up a ratio, 5.45 divided by my period, and then I multiply that because it's just a ratio of the amount of time that I have versus the full time it takes. Multiply that by 360. And let me try that again. This is milliseconds, I forgot, but even minus 3. And I have 117.72 degrees. Would you say that that's pretty darn close to 120?
Yeah.
And you could do the same thing over here. If I drag this one over here and got it approximately to the peak, I had 5.45, now it's 5.68. Again, you're just trying to eyeball it as best you can. If you wanted to be precise, you could keep zooming in, but this is close enough for me. So the question is for number 6, are the waveforms sinusoidal? What's your answer?
Yes.
So highlight yes. The next question, what is the approximate phase shift between the voltage waveforms?
About 117 degrees.
Yeah, 117.
120.
Again, that's not precise. I would probably round that up to 120 just because
Right.
it's because if I did it at 5.68 now, so let's redo this at 5.68. Say 122.7. So right in the middle is about 120. So I would put 120. Okay. So now we're going to do one thing. We're going to take our power supply here, and you can see our voltage is around 120. Our frequency is 60 hertz. I'm going to go back here and I'm going to change my speed to 1,000 RPM. What do you think is going to happen when I change that to 1,000 RPM? What do you expect to happen?
For the
Will your time decrease?
The phase shift?
Yeah.
It actually stays 120 degrees. We'll see that in a minute. Two things will happen. The first thing that happens is, remember that equation EA equals K times phi times omega? Well, K and phi aren't changing.
EA will drop.
Yeah, EA drops because my omega drops. The other thing that's going to change is, you remember when we looked at synchronous speed, and we can determine the electrical frequency by taking the number of pole pairs and multiplying that by the equivalent mechanical speed. So if my mechanical speed drops, my electrical frequency is going to drop. So let's go ahead and turn that in. This frequency should reduce and this voltage should reduce. So let's do that. And there you go. The reason why you don't see any frequency here is because we don't have a full sine wave. So let's change this back to 5 milliseconds. Now your frequency is down at 33 hertz. And look at my voltage. It went from around 120 to 67 or so, give or take. So the question on the table is, how do the amplitude and frequency of the voltage waveforms vary when the speed? Well, the frequency changes and the amplitude changes. The amplitude changes because of EA equals K phi omega, and the frequency changes because it just takes us longer to get around that shaft, to rotate around that shaft before we can go ahead and get another sine wave, another pulse. So it takes more time. It still takes the same number of revolutions, but it takes more time for us to get there. So that's why the frequency decreases. Now, going back to what Braden said, what about the phase shift? Phase shift. Let's take a look over here. And let's take a look over here. So the time is 9.84. So let's go back to MATLAB. And 9.84 e to the minus 3. We're going to divide that by, now our frequency is 33 hertz. It was 60, right? So now it's 33. So we're gonna actually let's put the t, let's put f equals 33. T equals 1 over f. And now my my phase shift, did I call it anything? I didn't call it anything. So my phase shift is going to be 9.84 or divided by my period. That, again, that's the amount of time. So I have a ratio of the amount of time I have between the total time to go 1 period, and then I multiply that by 360. Oops, I forgot the e to the -3. Sorry about that, folks. Would you say that that's pretty close to 120?
Yes.
Yes.
Yeah, so interestingly enough, it still is a balanced three-phase system that's at 120 degrees. And because the phase shift is not determined by the speed, it is determined by the actual physical location of the poles. Where they are physically located on the rotor, or on the stator, I should say, is what determines the 120 degree phase shift. So speed does not have any impact on 120 degree phase shift. Okay.
So-
Okay. Questions on that? Okay. So let's go and bring up our meter here. And let's look at I3 exclusively. And one thing to note, I3, it's a DC current. So don't forget to convert this to DC. And I'm going to go ahead and move this way down over here and pull that up so I can still see I3. Turn that on continuous refresh. And you can see I'm getting 0.668 or so milliamp or 668 milliamps to get this voltage. Now watch what happens when I decrease this value, okay? If I decrease this value, it's going to decrease the current, the excitation current. What do you expect is going to happen to these waveforms? Will they get shorter or longer? Remember, this is only changing the magnetic field. It only changes the phi, and EA equals K phi omega. Omega is not changed at all. So will these waveforms elongate at all?
No, they'll get shorter.
Are you sure they're going to get shorter? Remember, this only changes phi. It doesn't change omega. The only thing that changes omega is when I change the speed here. So changing this is only going to affect that value of phi, which means as I vary that value of phi, it's going to vary the value of EA. It's going to increase it or decrease it proportionally, essentially. It's not going to change this, and it's not going to change the phase shift. Again, the phase shift has everything to do with the fact that the poles are spaced 120 degrees, essentially mechanically apart. So let's start to drop this and look what happens. Oops, I gotta turn this on. Sorry about that. Can you see how it drops down? It was at 0.668, give or take. So here, down to here. Magnitude was around 67. Now I'm at 55 for my RMS magnitudes. And also, my field current has dropped. So varying the field current, all that does is change the magnitude of the voltages. It doesn't change the speed. See, it's still 33 hertz, and we're still getting approximately 120 degree phase shift. Okay. So that's the reason why the system performs the way it does. We're just changing phi. We're not changing anything else. Okay, questions? Because we are on to step 9, which means we can stop that. We can turn off our power here. Questions?
Oh,
No, almost set for now.
Okay. All right, so now we're going to modify this diagram. So we're going to delete a bunch of wires here. Delete. Delete. I'll leave that one there for the time being. I'll leave that one there. And then I'm going to I'm going to keep these connections here because I still want a Y connected machine. But now if you look across the synchronous machine, the voltage I'm measuring is across E1. So it's across two phases. And now I'm going to put a resistor in series with my meter to be able to more directly control the amount of field current in there. So first thing I'm going to do is I'm going to I'll move this wire here and here. And this wire goes from here to here. So now I'm measuring the line voltage output. So I'm measuring between two lines, line 1 and 2. And now I've got to go ahead and interrupt the circuit here. So I'm going to actually move this wire to my resistor here. And then I'm going to set them up in series, each of these resistor banks. And then I'm going to connect that over here. And then I'll just toggle on these switches. We'll start off with those on and then that off. Okay, so I'll give you a second to get caught up. Make sure you're on the same page with me. I got somebody here at my door, so just give me 1 minute and I will see what they. All right. So here's a couple things, right? We're monitoring E1, that's voltage. We're also going to be monitoring the DC current in here. Now, another really useful thing that we want to monitor is the speed of rotation. So if I zoom in a little bit and you look at one of these outputs, you will notice there's an N, analog output. So I'm going to run that 8 into, you can see there's an N right here, because it's smart enough to know, this data acquisition device is smart enough to know that this N is speed and it'll display it correctly in your metering window. The other thing that you have to do is that you have to have a common ground. So I have to have my analog grounds consistent, otherwise they won't provide the same reference. So you want to make sure your analogs connect here and your torque value is here. So now we can go ahead and set up our meters. So I've got I3, I've got E1. I'm going to go ahead and put meter 2 on, but I'm not going to do E2. I want to go the frequency of E1 because I want to actually calculate frequency. And then the last thing I'm going to do is, if you look over here, you see it says AI8/N. I'm going to turn that on, and that will be displaying my information, because if you look at what you're trying to plot in this step, it actually tells you frequency meter will be used, the speed, record the output voltage, the frequency, the field current, and the speed in the data table. So those are the 4 parameters I'm going to use. So now what I'm going to do is I'm going to bring up this here, and I'm going to display my data table. And the parameters that I want to do are, oh, sorry, you have to turn off the oscilloscope because it tries to outsmart you. So we'll turn off the oscilloscope. And now we'll do the parameters. I want E1. I want the frequency associated with my E1 input. I want my my speed. Okay, so that's I3. And then I want my speed, which is right here. Okay. You could also just grab it from here, but what I'm trying to do is show you in the lab how you get that information. So those are the 4 parameters that you're going to click on. You're going to hit apply, and now you have those parameters here. Okay. So the first data point I'm going to do is when my meter, I'm going to go from 0 to 450 field current, 450 milliamps of DC field current. I'm going to start at 0. So I'm going to turn this on. I've got to change my speed to 1800 RPM, I believe. So nominal speed of the synchronous motor. So that means I have to set this to 1800 RPM. And I start it. So it'll go up to 1800 RPM. And then I'm going to go ahead and I'm going to minimize this once that's studied out in speed. Looks pretty good. Now I'm going to go and start doing my measurements here. So I've got to. Why don't we do anything? Hold on just a second. This spin. Oh, okay. So it is reading because you see it says 1800 RPM. So with a field current of 0 milliamps, my voltage and my frequency are 0. So I'm going to do my first recording by hitting that button. So I've got no field current, I've got a frequency, and I've got a voltage. And I don't think there's a way to move these columns around and kind of stuck with it. Because what we're trying to control, the independent variable is field current. These two are dependent. So now, move this over here, and I'll move this over here so we can kind of see it all on one screen. I'm going to go ahead and throw my switch over here. And I want this to be 45 milliamps. So I can't get there from here. So let's see if I can tweak this up a little bit. Nope, not going to work. So now what I'm going to do is instead of having a 300 ohm in here, I'm going to put 1200 ohm. So that's getting me closer, right? That's getting me down to 0.7, but I'm not there yet. So let's do another one in series. Oh, that's pretty close. So now I'll do a 600 here instead of a 1200. And there we go. I now have my next value of DC field current. So this is stabilized. It's not exactly 1800 RPM. It's pretty close. So now I'm going to hit record my second value. Everybody understand what I'm doing there? I'm just trying to get us 10 separate points.
Yeah, my current isn't going up. Oh, I don't have my power supply on. There we go. Never mind.
Okay. Braden, or working out okay?
Yeah,
Okay. Am I going too fast or? That means yes, right? Nobody's saying anything.
I just
Yeah,
did.
just give me one
I
sec.
got it.
Sure. Please let me know when you're ready to proceed.
I'm ready whenever.
Yeah, I'm good.
Okay. So now I have to take this to 90. So I'm going to go ahead and put the 300 on. Take the 600. That doesn't get me there. Now I'm going to put a 300 in here. Turn that one off. And I'm going to try another 300. Turn that one off. So I'm at 122. So I can't get perfectly there. So now what I need to do is I'm going to adjust this to see if I can get there. So that just increases it, right? You can see how that increases the current. So what that tells me at that point is with these 300 ohm resistors in here, I'm kind of out of luck. So does anybody have a suggestion as how do I can get more field current through there? I mean, less field current through there. Let's put the 1200 back on and let's see. All right, that's 0.7. So now let's see if I can tweak this up. I'm not going to get there from here. So let's try the 600. So literally it's just, you can see it's trial and error, right? So now I'm at 109. So let's see if I can bring it down to 0.9. Ooh, so close. Not quite there yet. So let's see, I'll put a 600 in there. There we go. I think we should be able to make it now. So now I'm at 0.082. So let's bring it up. How about we call that close enough? 0.089 is close enough for me to get the 0.9.
Yes.
So
What resistor values did you use again? Sorry.
I used a 600, a 600, and a 300. Good to go?
Yep.
All right, so let's put 300s in here. And you could leave the 600 on. So you can see I'm at 145, 140. I need to get to 135. So let's back this down a little bit. And there's my 135. So I'm going to go ahead and record those. So all I now have is I have only 300 ohm resistors in there. And I adjust my exciter rheostat just a little bit, or potentiometer a little bit. And I get to 135. Okay. Can we continue?
Yep.
All right, so I got to go to 180 is my next one. So if I crank this all the way to max, I'm not at 180. And I can try and put these on to see if I get 180. So you can see I can get there from here. So I put those on, and then I'm going to back this down a little bit. Here's my 180. So I flipped all three of these resistors on, so all three are in parallel. All three of these are in parallel, and I still just have a 300 ohm resistor. And I get to 180. So hit record. And I have 180. Ready for 225?
Yep.
Okay. Put that on, put that on. I'm close. Let's see if I can do max. Uh-oh, I'm only at 218 with all three of these switches up. So what should I do now? I can't add any more switches. They're all on. So what's my next step? Well, my next step is, instead of forcing the DC current to go through here, why don't I just move that over here? So I'm completely bypassing this resistor bank here. And now, let's see if I turn off this one and this one. I'm at 233. I need 225. So I can bring this back a little bit. And there's my value that I have. So to get this one, I actually had to take one resistor set out of the sequence there. And now all I have is this 300 ohm resistor and these three in parallel. And then I adjusted the potentiometer to get that value. So I'm going to hit record and I get 225. Everybody following that?
Yeah.
Yeah.
Okay, now try to go to 270. Can't get there from here. So you can see I can try toggling these on here. So this one and this one. So I can get to 270. So I'm going to go ahead and bring this down just a little bit. Get to 270. And hit record. Next one's 315. I've already seen that I can't get to 315 with all these on. So just like I did before, where I took one resistor bank out, I'm going to do the same thing over here and bypass that. So now I've got to do 315. Let's see if I can bring this all the way down and get to 315. I can. So let's put 315 here. Here's my 315, and all I have is all three resistors on in one sort of bank. All three are in service. And I have my rheostat set to this pretty minimum value. So I hit record. Everybody following that?
Yes.
Okay, 360 is next. Looks like I'm going to be able to get there with a configuration. So all I did was just adjust the rheostat. So I hit record. Now 405. Close enough for me. Hit record. And the last one I'm going to do is 450. Let's see if I can get here. Can't get there from there. And all three of these resistors are online. So the only thing I can do is bypass this resistor bank by dropping to this terminal here. So here's my 450. Got to go all the way back. Well, this one I can't even get. I'm kind of bouncing around it. So here's another option, right? So it looks like I can't get there from here. So what I'm going to do is I'm going to delete this. I'm going to run this wire over here. And then I'm going to run these in parallel with each other. So I just have more resistive banks available to me. So all I have now is I've got these two resistive load banks. The wire doesn't grab. These three are up, these three are up. So my current now is 368. Let's see if I can adjust it and get to 450. Yep, it's between here someplace. So I'm going to get to 450 by doing this connection, right? Oops. Yeah. Close enough. And that's the data collection that we need to use or do for this step, which is step number 13. Questions on that?
Nope.
Nope.
Okay, so now I'm going to export this data as a CSV file. So we'll call this lab 5 underscore. This is step 13. Hit export. And then I'm going to bring up Excel. And I'll just do a new file for you all. So I'll do a blank notebook. Actually, I should open it. So I'll do new. And it's going to be open. And where's the location of that file? I didn't see that. Maybe it's in the downloads. Let's see. Yeah, so it's in downloads. So I'm going to go ahead and open this file under my downloads directory. And it's not showing here because in Excel, it's only looking for Excel files. So I'm going to go ahead and look for all files. And here's my text file right here that I just created by exporting it. I hit open. And it's going to be comma separated variables. So I hit finish. And the nice thing about exporting a file is I have the voltage, frequency, current, and here. So I'm going to change this. I'm going to say V line to line. I'm going to have frequency. I'm going to say IF for my field current. And this is the N for the RPM. Now it's asking for a plot. Let's see. It's asking for a plot. I'm just trying to find it. Oh, wait a minute. Did it ask me for another data point? Oh, yeah. So I'm sorry. One more data point. I forgot this last data point. So let me close this one. So don't save. So one more data plot, which is everything is on, it's fully on. So I forgot to record that data point. So at this point, I'm going to run the maximum. So I'm going to bypass this entirely. I'm going to run this one. I got to delete that wire, it's on top. So I'm going to bypass that and go here. And then I'm going to turn my field current up to the max. Here's the maximum field current that I can have. I'm going to record that. I don't know why it skipped that many, but that's fine. And now I'm going to shut the unit off. So this is going to go off because running that much current into it would be a lot. And then I'm going to stop this rotation. Okay. So now I've got my data table. Now I'm going to do the same thing. I'm going to export it. So I'll just export it with the same name. And then I'll open it up in Excel. And finish that. Oops, why didn't it? Maybe it saved it as a different file name. Let me double check. I thought I only saw one. Yeah, it's a different name. Sorry about that. So I'm going to open. Not that one. So that's the new one. And then you'll see the extra data points in there. Once I do the finish, I'm going to delete these 3 rows. So now I'm going to have V line to line, frequency, IF, and this is going to be my speed value here. Okay, so now what I want to do is I'm going to go ahead and do a plot. And my plot is going to be, well, so it says record the frequency. So the frequency is about 60 hertz, wherever we had a reasonable enough voltage to get it. So the first question is frequency is 60 hertz, is number 16. Number 17 is N, which is 1800 RPM, multiplied by the number of poles per stator winding. There are 4 poles or 2 poles per stator winding. So P would be 4. So I go N, 1800 times 4 over 2 divided by 60 gives me 60 hertz operation. So this validates that I've got, I should be getting a 60 hertz output based on a speed of 1800 RPM. Now I'm ready to go ahead and do the graphing. So I'm going to do a plot. It's going to be output voltage as a function of field current. So I'll show you how to do this pretty efficiently. If you, I'll save it as an Excel spreadsheet just because it doesn't lose any fidelity. So we'll call it an Excel workbook. So now I'm going to highlight these columns for this data. Then I'm going to also hit my control button and highlight this data. Then I'm going to insert an XY plot, which is here. And what I want is my dependent variable to be on the Y-axis and my independent variable to be on the X-axis. Field current is shown here, but that's the independent variable. Remember, I'm controlling the field current and then my output is the voltage. So I have to change the XY axis. And so I do that is I select the chart or the curve. I right click and then it says select data. Then I edit. And now I'm going to just go ahead. So my X values, I want to be my field current and my Y values, I want to be the voltage. So here's my X. And here's my Y. Click OK. And there's my curve. So this shows you that in your synchronous machine, you actually, and it shows, there's nothing here because the machine's not strong enough, but it shows you fairly linear, and then you start to get some saturation, so it starts to peel away. So this is essentially what we're seeing is what's called the open circuit characteristic of this particular machine. So we can add a little bit of data to it. We can do a chart design, and we can add a horizontal or let's start with the horizontal axis. We'll call this field current. Then we can put DC amps. And we're going to go ahead and add a vertical axis now. And this is line to line output voltage. And this is AC volts. And then the chart title is, oops, too many buttons, sorry about that. I guess it's leave it, so let's put it back over here. There's the chart title, so we'll add that. Oh, I'm not showing the title. The chart title above the chart. So this is going to be field current versus terminal voltage. And that's the curve that is expected for number one. Everybody following along, or am I going too fast?
Following along.
I'm following along.
Okay. But if you remember what we looked at in class yesterday, when we looked at that Northfield Mountain project, where we had that generator data, and we looked at the bottom or the end where the curves were. That's page 8. Remember we talked about this curve right here? That's the no load or the open circuit characteristic. That curve is essentially what we just developed here. Not as smooth, we'd have to do a lot more data points, but this is the curve. And we actually could change the curve type. Let's see, how do I change the curve type easily? We might be able to do a smooth fit. Once it's already selected, a smooth line. Guess it doesn't want to do a smooth line. It kind of does a little bit here, but it doesn't do a great job here. But that's essentially how they develop an open circuit characteristic. That curve right here is what we just created. And if you look at it, it is excitation current, IF, versus the terminal voltage or the no load voltage. That's exactly what we have here. So we just rebuilt that curve. So the question on number 19 is, why is this linear here and then it gets to be non-linear? Anybody know why? What happens in magnetic material? Why do we have to look at graphs of magnetic material as opposed to just having a bunch of equations? Remember the concepts of permeability and
You like only push so much current through before you reach saturation.
the flux?
It's
Yeah,
like-
exactly. We push so much flux and we start to saturate. So we need a lot more field current to go. So if we look here, we go from a little under 100 volts to a little over 150 volts. And then if we go over here, you see we're a little over 150 volts. So basically, increasing by, the same 2 milliamps, we only slightly increase. So we are in the saturated region. Okay. That's 18 or 19. Shall we move on to step 20 or am I going too fast?
Nope, we're good. I'm good.
Good.
Okay. So now we have to go ahead and we have to flip my switch here. And I'm going to turn on my current so that I'm only getting 300 milliamps. So let's see if I can get there by turning this down. Can't get there from here. So I will pull, I'll delete this wire. And I will pull this one up to here. So that's the minimum. So I can't quite get there from here. So let's take off this one. And let's see if I can get to 300. 300 is right about, yes, I can get there. Okay, so that's my 300 amps or 300 milliamps of field current. Now I'm going to go ahead and I'm going to measure my output voltage. So that doesn't change. My field current, I have that. My frequency and my speed. So all those same parameters I have. And I'm going to start the prime mover speed at essentially, well, we'll start it at 200. I guess we could start it at 0. So I'm going to go ahead and clear all my data. So let's stop that and clear my data. Let's see if I do it all at once. Clear data table. So we're going to start from scratch, and my RPM is going to be the only thing that changes. So right now I'm at 0. So I it's fine, but I'm going to go ahead and record. Oops. A value at 0. Now I'm going to take this up to 200. And I'm going to start it. So my field current doesn't change. The only thing that changes is the speed of operation. And that looks like it's pretty well set on that value. So record. I go to 400. Wait till it stabilizes out. I guess I can heat it up a little bit here. Looks like I stabilized. I've got 400. Now I go to 600. Wait till it stabilizes. Okay. Oops, wrong button. Sorry about that. 600. 800. Thousand. And I'm just doing this. You can feel free to do it along. It's not too complicated. Pardon me. Sorry for sneezing in everybody's ears. I thought I took the wrong mic ear off. 1200. Record. 14. Good. 16, getting closer to the end. Record 2 more, 18. And last, 2000. And there we are. So now we can stop. Switch off our power supply. And now we have our data table. Okay. So we have our second data table. And this is going to be, we'll export the data again. So we're going to go lab 5, and this is step 22. And we'll do the same process over again. We'll open up the data. Back to downloads. Open that up. And again, that's just a step that we do CSV, which is comma separated values. So this is E line to line, frequency, IF, And this is my speed value. So now we're looking for some curves where we're calculating voltage or line voltage versus RPM. So remember, the only thing that we controlled was the speed, and then the voltage was determined. So this is the value, that's the X value. And this is the Y value. So we're going to go back in and insert a plot. And you can see it's backwards, right? This is our speed and this is our voltage. So we're going to toggle those again. Same approach. We select our data. We edit it. This is our x-axis. This is our y-axis. We change our title to, it's funny because I click on things and I tell it to do stuff, but it just seems to ignore. Why is it doing that? Sorry about that, folks. Let's see if I can do it this way. All right, it doesn't want to do that, so let's try that again. Here's that set of data. My fingers aren't working today. That data, insert my XY. Now I got to select the data. I don't know why this is acting so goofy. There we go. Oh, maybe it's doing it because it's a text file. Maybe that's why I'm having some issues. So let's see if this fixes it. I did it before where it didn't have any issues, but now it seems to be having some issues. So, all right, this doesn't work. I don't know what else to try. Why is it disappearing? Anybody know why that's disappearing? It's like it wants to put it down, but then it doesn't show a chart.
I have no idea. Not the greatest at Excel.
Well, it's like it's weird because I select the data, I insert an XY plot, and I see it here for a moment, and then I click it and it just disappears.
Is it getting thrown somewhere else in the, like, out of the field of view? Oh no.
It's missing object description. Add a description. I'm happy to do it. I don't know.
Weird.
All right, let's close this. Maybe it's just having some hard time. Let's close this one. Let's try opening it again. I'm going to start back from scratch here. Okay, so save as. I'm just going to save over the existing one I developed. All right, now let's try that again. If this doesn't work, I don't know what else to try. Because it should be pretty simple. Huh. I don't know what I did differently, but that time it seemed to have not lost its way. So let's edit it. Here are my X values, is my speed. My Y values are my voltages. Okay. My chart title is speed versus line voltage. And then I'm going to add access titles, speed, and then This is line voltage. Okay. So this curve is really interesting, right? Because what you see, I didn't change the field current at all. The field current was fixed at 300 milliamps. But notice that EA equals K phi omega. Look what happens. It's pretty linear, right? As I increase the speed, I'm not changing the flux, right? The magnetic field isn't changing. So the speed is not, it's just a proportional constant. I don't try to push more flux through a magnetic field that I'm going to start to saturate. This has nothing to do with saturation. This is just that omega term. So this is a linear relationship. As I increase the speed, the voltage increases linearly. And that's how, describe how the synchronous voltage output varies as the speed varies. They vary linearly. As my speed increases, the voltage increases proportionally. Okay. Now, I'm going to do another curve where it's going to be frequency versus speed. Insert another XY. Okay, same deal. It has X and Y backwards, so I just have to switch that around. My X is my speed, and my Y is my frequency. Change the title. Frequency, sorry, speed versus frequency. And here's speed. And this one is frequency. That's right. Now, what can you say about speed and frequency?
When speed increases, frequency increases linearly.
Yeah, it's a linear relationship, which again makes sense because the speed is directly proportional to the frequency. It has nothing to do with saturation. You're not increasing or decreasing any magnetic field. So nothing to do with it. So those are a linear relationship. And that's it for the lab. Questions? All right, well, I'm going to stop the recording unless you have questions and give you some time to look, work on the lab. If you are done with the lab and you get all your answers, you can bag out of the lab, but if not, you're welcome to stay. We have till 3:50, so we have a little bit of time to go ahead and do that, but I will stop recording as of now.